Okay, welcome back. The last video was all about if all the radio data is in a file, it should be really easy to study, like with a spreadsheet program, much like Microsoft Excel or even the free LibreOffice Calc. We used the second one and gave it a try. I had troubles really finding a whole lot of evidence of hydrogen. It was sort of there, but it kind of in a small bump. So I came up with an idea for different kinds of computer programs to look at, analyze this data. We follow my cursor in the top left-hand corner. Sure enough, there's some hardware. It has a coax cable that goes into a radio. That radio is controlled by some kind of computer program. There are several to choose from. I prefer the one that I wrote called ezCall, C-O-L for collect. It writes it directly into a data form called ezRA.txt files. They have energy of each sample has power spectrum. There's a program called ezFix. All the programs, of course, start with EZ in Easy Radio Astronomy. There's a program called ezFix that can modify those data files and make it a little simpler to change the latitude, or maybe you got the time wrong. You want to change the name of the telescope in it. And ezFix is a program that allows you to do that or even automate it. We looked at that .txt file with something like Excel, a spreadsheet program, and sure enough, we could see graphs. That is a human readable .txt file. I'm suggesting we could write a program called ezCon for condensing, C-O-N for condensing, and other programs like ezPlot, ezSky, ezGal to get more information from those original data files. Let's take a look. What would we write this program in? Very popular these days and known by many high schoolers is Python. It seems to be robust enough. It has enough information. It's quite human readable. There's lots of information on the web. It seems like a good choice for what we need to do. Lots of libraries to support the things we want to do here with radio astronomy. Okay, how would you use it? If you were standing in a directory called ezRA base, perhaps in a subdirectory called demo, in the way that I'm suggesting you install it. In Windows, you would first type py for Python. In Linux, you use a different word, and it's Python 3 is required. Back here in Windows, you have to run a program. The way I suggest is you go up one directory, ... over into the ezRA bucket of files, and choose the ezCon, C-O-N for condense, .py, Python program. It's the same spelling down here in Linux, except now you got // instead of backslashes, as you do in Windows. That condensing program needs to go get a data file. Might be in your data directory. This one is N0RQV-8 for the 8-foot dish. It was in 2023. The last two digits are 23. The month was 02 for February. 9 was the day of the month, underscore, and then 00 was the first UTC hour that it started with. If it started an hour later, it would be underscore 01 for the first hour. And we know that these data files are readable with an editor or even a spreadsheet, a .txt file. On Linux, it's the same, but there's a slash. This one's forward versus backslash in Windows. Windows sometimes doesn't care whether it's a forward or backslash, so good luck and all these good things. But it's a fairly simple idea. You run Python, you specify a program, there are several, and you specify perhaps a data file or maybe even a whole directory of data files. And what do you get? Whole bunch of samples. We did this before. We looked at all these 256 red dots going across the page. They start out low in frequency with low values, and up at high frequency, they have low values. In the middle, there's this three humpy hump thing going on. That is more controlled by the electronics, the filters, the amplifiers, and even the receiver electronics. We can remove that later. Software-defined radios, SDRs, the way they work, they often have a mathematical little quirk that the center frequency has a spike for its values. But sometimes you see a bump from the galaxy. Sometimes it's on the lower frequencies on the left, sometimes it's on the higher frequencies on the right. It can be of different shapes, or it might not be there at all. 256 numbers going across. If we think of this like a slice of bread shown here, down at the bottom, there's low frequencies with low values, high frequencies with low values. In the middle, it wiggles around and has that little spike in the middle. If we put the low frequencies at the bottom of the page and the high frequencies at the top of the page and insert this slice, look at the top of the slice, it would look like this. On the Y scale is frequency, going from low negative numbers up to high positive megahertz numbers. This sample is represented by this green line shown here. Starts out with colors like black and purple. We look over here on the color bar on the right, that black must be a low number. Purple's just a little bit brighter. The middle colors are yellow. Those are big high numbers. And way up here at high frequencies, that slice of data had black and purple, again, low values. So there's our slice of bread stuck in there, right next to another slice and another slice and another slice. All these samples are straight up and down vertical lines on this graph, laid side by side, starting with sample 0 down here, counting all the way up to a high number. The bottom says the last one is sample 907. So there are 908 samples laid side by side, like slices of bread in a loaf of data, from 0 all the way up to sample number 907 up at the top. We already know that vertically there are 256 frequency bins from low frequency up to high frequency. One sample here next to all these other samples. All right, let's get all this graffiti off of here. What do we see? It's kind of a whole bunch of bright numbers. It's got a stripe down the middle, maybe that little spike. But there's also some kind of ghostly thing going on in here. I see kind of a blob. There's some other blob over here. And if your video monitor is good, maybe you see some kind of sinusoidal wiggle in here. But gosh, it's faint. Let's keep studying it. There's also some other weird stuff going on. It goes along here, and then I see all these up and down vertical lines, kind of darker than the others. They're like curtains hanging down across all this. It then happens all the way across the whole sample from high to low frequencies, but only on certain samples. Something's varying in time. What do? We go back to what we learned long ago. What's the difference between these two pictures? Sometimes you see nothing on the back of the truck, and sometimes you see a something. Nothing to something comparison. Sometimes there's a cloud in the top right, and sometimes there isn't. We notice the difference by comparing the two pictures. Sometimes there's a something to something difference. This is an unhappy truck. And this is a happy truck. So something versus something again, but different. Let's use that concept and find out more about this data, comparing one to another. We talked about those curtains up here on this part of the date. I've circled where they're rather visible. There's a way to do something about that. We can see all this hydrogen stuff going on in the middle, or maybe ghosts of it. But we don't see anything up here at the high frequencies, and we don't expect anything down here at the low frequencies. Let's compare the stuff in the middle where all that hydrogen is, that information, to the top part, the top 60 frequency bins where there is no hydrogen, and also to the lowest 60 frequency bins. This part in blue, here's a sample. The blue part should not have hydrogen in it, top and bottom. But the red part in the middle should have hydrogen. So let's compare the blue parts to the whole sample. If we take the average of the blue values, top and bottom, we could make a value for each sample made up of the average of just the blue parts, a number for every sample, a baseline of the background, one number for each sample. If we take every value in the sample and divide it by that one baseline number that we found, one number per sample, what happens? We've divided the whole vertical sample, every value, by that baseline. And it kind of made things smoother. Suddenly these curtains are gone that I was circling up here above. It looks better. I don't think it made anything brighter, but at least it kind of cleaned up the image and got rid of some of that noise. Because we started with the antenna signal and used some kind of baseline of the background information, I call this calculated signal ant B. This is not a signal from the sky like antenna. This is some math occurred on it, a calculated signal. All right, what else can we do like that? There's all this noise stuff at the bottom, and at the top, some bright colors. The first suggestion is let's compare every antenna sample, all that yellow stuff, to one reference. Let's use sample 0 as that reference. Let's compare every sample to its neighbor, sample 0. What does it look like? If we take every vertical line sample and for every one of those frequency bins, divided by the corresponding frequency bin of the reference, the sample 0 in this case. What happens? You get some weird graph, but we're starting to see more. There's kind of a bright blob here, and something's going on over here. It's got a lot of noise in it, but all that strange coloration at the very top and at the very bottom seems to have disappeared, although we still got these curtains. It goes along with a bright red color, then it goes down to blue, red, blue, red. It alternates with those curtains that we saw before. But we kind of know how to fix that. We look at all the frequencies up here and down here and get a baseline of this signal, one number for every one of these samples. And for the whole sample, all those numbers, we divide each one of them by that baseline, just like we did before. And we get this. Well, that improves it pretty well. Most of the background is kind of a bluish. We got this thing showing up like I never did before. There's a blob over here, and now we start to see this sinusoidal pattern more. This signal started out with the previous one. Let me back up. It started out with ant R, something to do with references, and the first letter of the alphabet's A. So ANT-RA, this is some intermediate calculation going on here. We made a baseline out of this and then turned it into ANT-B. ANT signals where all the information came from. Something about R for reference, and not the letter A, but the letter B, the second letter, is this calculation's signal's name, ANT-RB. And it came out okay. Was there something strange about sample 0? Is that why this thing has so much noise in the background? Let's pick another one. Out here in the middle of nowhere, how about sample 495? Let's compare every antenna sample to a reference. Let's choose as that reference sample 495. Here's sample 495 out in the middle of nowhere. Let's take every vertical line sample, and for every frequency bin, let's divide it by the value, the corresponding frequency bin value in sample 495. Just like before, we get this intermediate calculation called ANT-RA, something to do with reference, and A is the first letter of the alphabet. We got this blob, we got these curtains, here's another blob. Much like before, we do a baseline on this signal, we play with that and divide every sample by that single values for each sample. We get ANT-RB. And this looks much like the blue plot we had just before. It's got a blob, it's got a blob. The background's getting better, but still there's a lot of noise going on here. I got another idea. Last time in the beginning for ANT-B, we were comparing where there was hydrogen to where there was no hydrogen. Let's take that to another extreme. Let's compare every antenna sample to a recent reference. Ooh, recent reference. So now we're going to have more than one reference. Instead of 24 hours ago, perhaps, let's do one quite recently. That recent reference should be from looking at the sky, same antenna, but way higher than where we expect any hydrogen. Let's look way up 3 megahertz higher than the center frequency was before and use that as a reference. So many references and looking at a place where there should be no hydrogen. If we look at the antenna, this is what we saw before, no change. We're looking at 1420.405 megahertz for this center 0 frequency. There's this faint thing we saw before. You've seen this picture before. What does the reference look like? Way up high, way beyond 1.2 megahertz higher. We went up 3 megahertz higher for the center frequency. So instead of 1420, now it's 1423.405. I need to change my program, get this better. Here, I see some curtains every so often. There's that stripe in the middle we talked about, that little spike. But I don't see any ghosts in here at all. This is a good reference sample. I don't see any hydrogen anywhere on here. Let's compare the ANT to the ref and see what happens. For every frequency bin of a sample divided by this reference, the corresponding value in this reference, frequency by frequency bin. We would expect there be different values. Sometimes we expect the hydrogen might have a value in blue. That's looking at the antenna. And the reference might be another value. Then the antenna, then the reference, then the antenna, then the reference. So we're alternating back and forth between looking at the antenna, where we expect to see hydrogen, and the reference where there is no hydrogen. But this is zoomed in. This is from sample 0 to only sample 50. I talked about 908 samples before. Let's look at the rest of them. If you look all the way up from 0 to the end of the file, here's the blue going along. And apparently it changes all the time. The temperature must change it. The probably creaks, vibration may change it. The electronics just wants to. I don't know, but it varies. But what's interesting is the place where there should be no hydrogen in the reference, it varies just the same. So it's going through the same conniptions as the antenna did. Good. It's sharing the same environment. That would be a good thing to compare to. And you can see the green line was just the connecting lines filling it in between all those things. This is what you do if you can divide every antenna frequency bin by the corresponding reference frequency bin for every dot shown on this page. This is the ezRA intermediate calculation. We play with the baseline of this sample and get a better picture, which is ezRB, slightly better, I will say. Wow, now we kind of have yellow things, and now I can really see the ghost of this hydrogen snake wiggling along here. Great. I got another idea. What happens if that reference frequency way up at 1423 actually receives something? Oh my gosh, it's getting in the way. We got interference. Why do we have to look at the sky? Let's just look at a resistor, some electronic part at the very front of the very first amplifier. Can we get a switch up there instead of changing frequencies? Can we still use 1420 as the frequency, but just look at a resistor after having switched from the antenna to the resistor, to the antenna, back to the resistor, alternating back and forth? That's what number 4 is. Lots of references, so compare to a recent reference and make that recent sample come from a resistor at the very front of the first low noise amplifier and use that spectrum as a reference to compare to. It will alternate back and forth. The blue is antenna, the reference is red in up above, blue, red, blue, red. This is the first 50 samples, just like before. If you look at all of them, it looks like this. As the antenna wobbles along and wiggles due to its electrical characteristics, it's got up and down over here. The reference turns out to do the same kind of pattern. It follows along, looking at the resistor. It goes down, it goes up, it goes down, it goes up, just like the blue line down below. Great. That's a good thing to compare to. We're comparing to the antenna signals where we expect hydrogen to something in a resistor that certainly isn't going to receive any hydrogen signal. What do we get? If we divide every frequency bin in the antenna by the corresponding frequency bin for the most recent reference, we get a pretty clear image. We're getting rid of a lot of the noise in the background. The background's getting bitter. This is the intermediate calculation, ezRA. It has a stripe down the middle and all kinds of stuff. If we go to we get a baseline off of here, we do the division, and we get ezRB, that second calculation, and it looks slightly better. Here's that ghostly thing going on here. It wasn't quite as bright as before, but I think that's confusion with these color stuff. This stuff at the bottom and this stuff at the top is giving a really bright color, which is screwing up our coloring scheme, kind of auto-scaling the color so that it's stealing all the yellow, bright information away from our data that we care about. So let's just cut it off. Let's take those frequencies and trim them. Just make them the value 1 and make them go away. 1 is kind of a blue color in here. That's what we do next. We run it into a different part of the calculation, and the bottom part and the top part, I just assigned the value 1. We weren't looking at that part of the frequency band anymore anyway. That improves the color scale going on here. We can see things better. The background's very plain and uniform. That's good. But we got this stripe down the middle. What can we do about this? Turns out the program has all kinds of ways to handle that too. Let's figure out which frequency channel that annoying little spike is on. Of course, there's a graph. ezRA has lots of graphs. One plot is for AntXT. I go to the next plot. Sure enough, there are a whole lot of values of 1 at low frequencies, whole lot of values at 1.0 at high frequencies. That's where I trimmed off other things. There's something going on here having to do with hydrogen, maybe something over here. But on every sample, there was a little spike, and they add up to a big spike. Which frequency bin is that big spike? Let's take this whole graph and turn it 90 degrees clockwise. So we put, actually, it kind of spins it around. We take these high frequencies and we put them up near the top as shown. These are the high frequency bins. Here's the lowest frequency bin down here. This way we can see kind of what number it is. It's just easier to pick out the frequency bin number with this graph. It seems to be about halfway between 100 and 150, might be near 130, somewhere in there. So we could start guessing, but the program is spitting out data to the screen all the time while it's doing all this calculation. It turns out for this graph, it spits out what we need to know. On that screen that comes out, for this particular graph, there's a whole bunch of data that's flying past. Let's zoom in and take a look at that. For this graph called ezCon, that's the program name, then there comes 3 digits, in this case 388. Then there's some kind of description of what that is. This is the signal called AntXT. We'll talk about that later. Something about by frequency bin, so not by time, but by frequency bin along the x-axis. And the average, apparently, of a whole bunch of those things. And then maybe rotated so we can study the radio frequency interference and pick stuff out. That's what this graph is. Holy cow. It has the indexes of the highest values of that signal. The highest value of that signal I call 100%. The program knows that the culprit that did that was frequency bin 128. And it's so bold as to tell you what to do. It says, hey, bud, maybe you should try some arguments on the command line like this thing and that number, 128. It took that number and wrote it down here. So I took the hint. In Linux, I had to write Python 3. I had to go up one directory, over into the ezRA directory, get the ezCon program. That's all just like it was before. And then we ran that data file down in the data directory, this particular file, .text. That's all like it was before. But I added what the program suggested, minus ezCon, something about changing the raw data, something about frequency bin, and hiding frequency bin 128. We're going to take the data from from frequency bin 127 for every sample and copy it onto the corresponding frequency bin 128 right next to it. We're going to take wallpaper from 127 and copy it right on top of 128 and just make 128 disappear. What does it look like? Well, this is what ends up. The same plot, but now it doesn't have that line down the middle. We got rid of that nasty spike. Okay, what we're talking about here is how we got data out of the sky in the antenna, and what we did through several different methods by comparing hydrogen information to non-hydrogen information, and extracted a better picture of what was going on here. We got blobs, we got curves. This is all relative power information, but we can start learning from it. This is the signal progression of how all those signals was calculated. Thanks for coming. That's an interesting video. I got more videos to start talking about next. Let me show you some more plots.